stand beside the world's largest diesel engine. It towers 44 feet tall, higher than a 4-story building, stretches 89 feet long, longer than a semi-truck with trailer. 14 cylinders, each wider than oil drum, fire in sequence, producing 109,000 horsepower. That's the power of 1,600 cars concentrated in one single machine. This engine burns 250 tons of fuel daily, moving 20,000 containers across oceans at 23 knots. How does metal combusting heavy fuel oil generate force pushing 90,000-ton ships through water? Why build engines this enormous when smaller multiples could work? Stay with us. You'll discover the brutal elegance of two-stroke combustion at massive scale, and the shocking secret of why these engines burn fuel refineries consider waste. The cheapest, dirtiest.
Our journey begins at Hyundai Heavy Industries in Ulsan, South Korea, the shipyard building these mechanical titans. The engine manufacturing hall spans 30 acres under single roof. Overhead cranes rated at 600 tons glide on rails, positioning cylinder blocks weighing as much as locomotives. Workers look like ants beside components. Watch the cylinder casting. Molten iron pours into sand molds, creating a single cylinder liner. Hollow tubes where pistons travel. Each liner stands 12 feet tall, walls 4 inches thick. The iron must cool for 72 hours. Rush it, thermal stresses create microscopic cracks that propagate under operation, causing catastrophic failure. We make engines that run 30 years continuously, explains Chief Engineer. No second chances if casting fails.
The crankshaft arrives on specialized trucks, a single forged steel shaft weighing 300 tons, machined to tolerances measured in thousands of inches across 70-foot length. Installing it requires choreographed precision. Hydraulic jacks lift the shaft while technicians align bearing surfaces. One misalignment of ½ inch causes bearing failure within weeks of operation. Picture the assembly floor. 14 cylinder liners bolt to engine block, itself a 40-foot steel casting, forming engine skeleton. Each connection uses bolts diameter of baseball bats, torqued to specifications requiring pneumatic impact wrenches lasting 5 minutes per bolt. Assembly takes 6 months, 12-hour shifts, teams of 50 engineers and technicians. One finished engine represents 200,000 man-hours, equivalent of one person working full-time for 96 years straight.
The pistons dwarf automobile engines. Each piston assembly, piston, rings, and connecting rod weighs 6 tons. That's heavier than full-sized pickup truck. The piston crown, exposed to combustion, endures temperatures exceeding 1,800 degrees and pressures reaching 2,000 psi. Material science pushes limits here. Watch piston installation. Cranes lower assemblies through cylinder tops. Workers guide them onto connecting rod bearings with millimeter precision. The piston rings, spring steel bands sealing combustion pressure, get installed by hand. Each ring expands under tension, slip during installation, and the ring snaps, injuring workers and destroying components worth $50,000. Veterans develop feel for tension, installing rings quickly yet carefully. 20 years I've installed 3,000 pistons, says one assembler. Still respect every one.
Now grasp two-stroke operation. Elegantly simple, yet counterintuitive. Unlike car engines firing every other rotation, marine diesels fire every rotation. As piston descends, it uncovers ports in cylinder wall. Compressed air rushes in, pushing exhaust out simultaneously. The piston rises, compressing fresh air. Near top, injectors spray heavy fuel oil. Compression heat, not spark plugs, ignites fuel. Explosion drives piston down. The cycle repeats. This two-stroke design eliminates valves entirely.
No camshafts, no timing chains. Fewer parts mean greater reliability. But it demands supercharging. Turbocharges forcing air into cylinders at 22 psi. Without pressurization, the engine wouldn't breathe. Turbochargers the size of sedans spin at 20,000 RPM, driven by exhaust gas. They glow red-hot during operation, requiring water cooling systems circulating thousands of gallons hourly. Fuel injection happens at extreme precision. Each cylinder consumes 16 gallons per combustion cycle, enough to fill your car's tank every few seconds. Injectors spray fuel as fine mist under 6,000 psi pressure. The atomization must be perfect. Droplets too large won't burn completely, wasting fuel. Too fine, combustion becomes explosive rather than controlled, damaging engine. The fuel itself surprises people. These engines burn heavy fuel oil, basically petroleum refinery leftovers after extracting gasoline, diesel, and jet fuel. It's thick as molasses at room temperature, must be heated to 240 degrees before flowing. Contains sulfur, metals, and contaminants that would destroy car engines instantly. But marine diesels tolerate it because economics dictate everything. Heavy fuel costs 40% less than automotive diesel. At 250 tons daily, that price difference means millions saved annually per ship.
Engine control happens from bridge via computer systems monitoring 600 parameters simultaneously. Engineers track cylinder temperatures, bearing pressures, fuel consumption, turbocharger speeds. The engine room, 3 decks tall, deafeningly loud despite ear protection, houses the mechanical orchestra. Walk the engine room during operation. Heat radiates from every surface. Metal creaks and groans as thermal expansion moves components fractions of inches. Across a 70-foot engine, that's feet of total movement. The crankshaft, visible through inspection ports, spins at 102 RPM. Seems slow until you realize this massive shaft accelerates tons of metal from 0 to maximum speed every single rotation. The forces involved bend physics. One chief engineer describes it, "This isn't machinery, it's controlled violence. We're detonating tons of fuel hourly inside metal box, converting explosions into rotation."
Maintenance happens at sea on schedules measured in years. Every 8,000 hours, roughly 1 year of operation, crews perform major service. They drain lubricating oil, 60,000 gallons per engine, replacing filters the size of trash cans. Inspect cylinder liners for wear using ultrasonic equipment. Pull pistons for ring replacement. The most dramatic maintenance involves crankshaft inspection. Engineers use magnetic particle testing, apply magnetic field, spray iron particles, look for cracks where particles accumulate. Finding cracks in 300-ton crankshaft spinning at 100 RPM means potential catastrophic failure. The process takes 4 days of continuous work while ship sits idle, losing $200,000 daily in lost revenue. But catching cracks before failure saves the engine worth $15 million. No shortcuts exist. We maintain like lives depend on it, states Chief Engineer, because they do.
Rudolf Diesel invented compression ignition engines in 1897, demonstrating fuel efficiency double that of gasoline engines. His original design ran on peanut oil. Diesel envisioned farmers powering equipment from crop byproducts. The petroleum industry hijacked his invention, optimizing for their cheapest product, heavy fuel oil. Marine applications began in 1920s. By 50s, diesel surpassed steam turbines. The two-stroke design, perfected by Sulzer and Wärtsilä through 70s and 80s, became dominant. Today's largest, the Wärtsilä-Sulzer RTA96C, produces power exceeding small city power plant. Just 14 cylinders generating 109,000 horsepower. 23,000 containers moved by single engine. 98% of ocean cargo moves via diesel-powered ships. These engines literally keep global economy flowing.
Carbon emissions seem paradoxical. These engines burn dirtiest fuel, yet achieve 48% thermal efficiency, converting nearly half consumed energy into motion. Modern cars manage 25%. The efficiency comes from slow operation and massive scale, allowing effective heat recovery through turbochargers and economizers. Here's the secret we promised. Marine diesels burn fuel refineries would otherwise struggle disposing. That heavy fuel oil, thick, contaminated, full of sulfur, represents petroleum industry's bottom-of-barrel waste. Refineries initially paid ships to remove it. Marine engines transformed waste into commodity. Today, heavy fuel powers 90% of ocean shipping. Those engines burning waste move 60 billion tons of cargo annually, generating 3% of global carbon emissions, while handling 90% of international trade. From refinery waste to global commerce, the cycle completes. We've built machines so large they boggle comprehension, burning fuel so crude it seems impossible, moving cargo quantities that dwarf imagination. That container ship horizon, powered by controlled explosions in cylinders taller than you, spinning crankshafts heavier than your house, burning fuel thicker than syrup. Engineering at scale where normal physics seems inadequate, yet it works reliably, efficiently, endlessly. These aren't just engines, they're the beating hearts of globalization itself.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena, lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious, invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust.
Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore. They process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries. Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers, rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal. Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained, recycled endlessly.
Carbon emissions drop 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
Every second, 32 tires begin service worldwide. Each survives 100,000 miles of punishment, heat, friction, road impacts before replacement. Picture mountains of rubber growing daily. 2 billion tires manufactured annually, weighing 25 million tons combined. That's every car, truck, aircraft, and bicycle on Earth demanding fresh rubber constantly. How does liquid petroleum become indestructible black donuts? Why do old tires refuse to decompose for 500 years? Stick around. You'll discover the shocking chemical process transforming oil into immortal rubber, and the jaw-dropping secret of where 85% of American-worn tires end up. Hint? It's beneath your feet on football fields.
The story begins in Southeast Asian plantations, where rubber trees grow in geometric rows, stretching miles. Workers cut V-shaped grooves into bark, collecting milky latex sap in cups. Each tree produces 2 ounces daily, barely enough to fill shot glasses. Natural rubber comprises 30% of modern tires. The remainder uses synthetic alternatives derived from petroleum. Massive chemical plants crack crude oil into monomers, butadiene, styrene, then polymerize them into synthetic rubber matching natural properties.
These facilities process 50,000 barrels daily, transforming black liquid into white crumb rubber. The similarity is uncanny. Petroleum-based rubber exhibits elasticity, strength, and durability rivaling million-year-old tree evolution. Chemistry replicates nature in months.
Next comes compounding, the secret sauce where rubber meets additives. Industrial mixers, standing 2 stories tall with rotors spinning at 80 RPM, blend rubber with carbon black, silica, sulfur, accelerators, and antioxidants. Carbon black, basically controlled soot production, reinforces rubber while providing characteristic black color. Without it, tires would be translucent white and fail within miles. Each tire compound contains 15 ingredients mixed in precise ratios. Tread rubber emphasizes durability. Sidewall rubber prioritizes flexibility. Inner liner uses butyl rubber for air retention. Formulations remain trade secrets. Michelin's compounds differ from Goodyear's, creating performance variations. Mixing takes 12 minutes at temperatures reaching 300 degrees Fahrenheit. The batch, weighing 500 pounds, emerges as uniform black mass ready for shaping.
Giant extruders force hot rubber through dies, creating continuous strips of tread, sidewalls, and bead filler. These machines operate like industrial Play-Doh shapers, pushing material through shaped openings at forces exceeding 2,000 psi. Tread emerges with grooves pre-formed. Sidewalls arrive as smooth sheets. Cooling conveyors solidify the profiles. Meanwhile, calendaring machines squeeze rubber sheets to precise thickness, measured in thousands of inches, coating steel cord and fabric plies. These textile layers provide structural strength. Modern radial tires contain steel belts running at 0 degrees to rotation direction, fabric plies at 90 degrees, creating cross-brace architecture. Workers cut these components into precise lengths, stockpiling thousands of parts daily for assembly lines demanding continuous supply.
Comes tire building, robotic ballet assembling 30 components into recognizable shapes. Cylindrical drums rotate while automated arms apply inner liner, body plies, steel belts, sidewalls, and tread in programmed sequence. Each component positions within 0.05-inch tolerance. Precision matters because imbalance at highway speeds creates dangerous vibrations. The green tire, uncured assembly, looks puffy and pale, lacking final tread pattern. Steel beads, wire bundles coated in rubber, anchor edges, providing mounting surfaces for wheel rims. These beads contain piano wire strength steel wound in continuous loops. Braking beads requires forces exceeding 5 tons, ensuring tires never separate from rims even during blowouts. Assembly takes 3 minutes per tire on modern automated lines, producing 2,000 tires daily.
Curing transforms green tires into finished products through heat, pressure, and chemistry. Massive presses, resembling medieval iron maidens, close around green tires. Internal bladders inflate with superheated steam at 350 degrees Fahrenheit and 200 psi. External mold segments, engraved with tread patterns, press inward simultaneously. This step is critical. Vulcanization. Sulfur atoms cross-link rubber polymer chains, creating three-dimensional molecular networks. Picture chain-link fences welded together at every intersection. That's vulcanized rubber at molecular level. The process, discovered accidentally by Charles Goodyear in 1839, transformed useless sticky material into engineering marvel. Curing takes 12 minutes. Afterward, tires emerge rigid with crisp tread patterns and permanent shape. They'll never soften or melt again. Vulcanization is irreversible.
After curing, quality control begins. X-ray machines scan internal structure, detecting steel belt misalignment, air pockets, or ply separations invisible externally. Uniformity machines spin tires at highway speeds, measuring force variations. Even 0.5-pound imbalance causes rejection. Ship tires must perform flawlessly at 120 miles per hour for tens of thousands of miles. Inspectors examine tread depth, sidewall finish, bead seating. DOT codes stamped into sidewalls identify manufacturing plant, date, batch number, critical for recalls. Modern tires undergo durability testing. Machines simulate 50,000 miles in 72 hours, cycling through temperature extremes, overloading, underinflation. Failure rate must stay below 0.1%. That's one defective tire per 1,000, because tire failure at highway speeds kills people. Performance testing pushes limits beyond consumer use. Test drivers race prototype tires on proving grounds, executing emergency maneuvers, sustained high-speed runs, extreme weather conditions. Sensors measure temperatures, pressures, wear rates. Data feeds computer simulations refining compounds in construction. Winter tires use softer compounds, remaining flexible below freezing. Summer tires employ harder rubber, resisting heat degradation. All-season compromises performance for year-round versatility. Racing slicks sacrifice tread patterns for maximum contact area. Professional race tires last 200 miles but provide grip exceeding street tires tenfold. Tire engineering optimizes contradictory requirements: durability versus performance, comfort versus handling, cost versus longevity. Every design represents compromises, balancing physics against economics.
This technology evolved from crude beginnings. Ancient Mesoamericans harvested rubber for balls and waterproofing 3,000 years ago, but material degraded rapidly. Charles Goodyear's 1839 vulcanization discovery changed everything. Accidentally dropping rubber sulfur mixture on hot stove created heat-stable material. The pneumatic tire emerged in 1888 when John Dunlop invented air-filled rubber tires for his son's tricycle. That innovation enabled automobile revolution. Cars needed shock absorption only inflatable rubber provided. Radial tire construction, invented by Michelin in 1946, improved durability 50% over bias ply designs. Today's run-flat tires, self-sealing compounds, and airless prototypes continue evolution. Annual global production exceeds 2 billion units, creating waste management crisis demanding solutions.
Carbon emissions drop by 62% using recycled tire crumb versus virgin rubber production. Industry saves over $41 billion annually through tire recycling. Processing old tires into crumb costs 70% less than manufacturing new rubber from petroleum. So here's the secret. 85% of American-worn tires avoid landfills through recycling programs. Shredders reduce tires to fingernail-sized crumb. This material becomes artificial turf infill, those black granules beneath football field grass that cushion impacts and improve drainage. Schools, parks, and stadiums nationwide walk on recycled tires daily without knowing. Crumb rubber also creates playground surfaces, running tracks, asphalt modifiers, improving road durability 20%. From petroleum to pavement to playing fields, cycle completes. Tires never die, they transform. That indestructible black donut refusing decomposition becomes humanity's accidental gift to circular economy. We've learned that immortal materials demand eternal responsibility.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy, making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Pierce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames means sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel, cobalt, manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine two giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton, or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly, before the fibers start to stick together. So, they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them. And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resonation. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1,800 degrees Fahrenheit, 1,000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a micro crack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point.